Welcome to our discussion of L'Hopital's rule. L'Hopital's rule is going to be a very easy technique for us to figure out what happens to functions at points of discontinuity and what happens to functions at infinity. So let's take a look at a typical example of where we could use L'Hopital's rule. Let's say we have the function f of x defined as the natural log of x over x minus 1, and we want to know what happens when we take the limit as x approaches 1. Well, whenever we're taking a limit at a number, the first thing we always try is we just plug that number in. But the natural log of 1 is equal to 0, and the bottom also gives us 0, and we end up getting 0 over 0. And as we've seen before, when we have things like that, we normally try and factor them out and remove those discontinuities. But that doesn't work with this kind of function because it doesn't factor. So there has to be something else we can do. Well, we can't use our normal techniques of factoring, and we see that we have the problem with this limit giving us the indeterminate form of 0 over 0. So we know we have to try something different. If we had something like this, we know we could factor it out. This is one of those typical algebraic examples with a polynomial over a polynomial. We factor it out, we cancel out the point of discontinuity right here with the x minus 1s, and then we're left with just x over x plus 1. We let x equal 1 and we get 1/2, and that's easy. This one we've seen before. Another example that we can't factor like our current example, but we were able to solve this one using some geometric proofs. And we did the same thing for the cosine of x over x. Well, this limit is not going to work with any of those other techniques, right? We can't solve it geometrically, we can't factor something out, but we do know that something's going on. And the same problem arises if we're trying to take the limit as x goes to infinity. So whether we're looking at the point of discontinuity or as x goes to infinity, we have no way of figuring out what's happening with this function. And that's where L'Hopital's rule comes in. So we know that when we have a rational function, f of x over g of x, right, we have some fraction, and we're taking the limit as x approaches a, that if they are both going to infinity, or if they're both going to negative infinity, or even if one's going to infinity and one's going to negative infinity, we know that the limit may or may not exist. Sometimes we can get an answer of 0 if the bottom grows really super fast, right, and ends up growing faster than the top. Sometimes we get infinity because the top grows faster, and sometimes they both tend to kind of grow at the same rate, and we end up getting that it levels off at some constant. So there are solutions. We have seen that there are ways to find solutions to other types of indeterminate forms of infinity over infinity. Now we're going to address a new family of these indeterminate forms. So as we saw before, if we had a polynomial, we had a very easy trick of just dividing by the highest power of x in the denominator and then reevaluating the limit at infinity, and all those fractional pieces with powers of x in the bottom all go to 0, and then we can figure out what happens. That's a great technique for when you have a polynomial over a polynomial. We don't have that with our current example. And L'Hopital's rule applies to this type of function. And in fact, L'Hopital's rule applies to all of them. So you can still use the previous techniques we've learned, factoring and dividing by x squared and doing all those types of things. But you can also, and here's the dirty little secret, you can also just apply L'Hopital's rule all the time to all of them. And it's a pretty easy technique. It's pretty quick, and it's probably going to be the technique you're going to want to do from here on out anytime you have a function over a function and you're taking that limit and you get that the limit goes to infinity over infinity or 0 over 0. And that's what it's saying here. Anytime you get 0 over 0 or infinity over infinity, you can use L'Hopital's rule. And basically what L'Hopital was able to prove is that the limit of two functions at a point A is equal to the limit of their two derivatives at a point A. And it kind of makes sense if you think about what derivatives really are, right? The quotient of functions is equal to the limit of the quotient of their derivatives, provided that the given conditions are satisfied. That is, right, what are the given conditions? F and g are both differentiable. The derivative of the second function doesn't equal 0 on the interval that contains this a that we're going to. And if we're going to infinity, it's the same idea. It's just a little trickier to wrap your head around. L'Hopital's rule is also valid for one-sided limits and for limits at infinity and negative infinity. So you can take limits as x approaches a from the left, a from the right, going to infinity, going to negative infinity, and it works for all of them. Now let's take a look at how and why this works. And to kind of see it, we're going to look at the special case where f of a equals g of a equals 0. And f prime and g prime are continuous, and of course g prime at a does not equal 0. And it doesn't really matter. The only reason why we're choosing this case is it gives us the 0 over 0 kind of indeterminate thing that we normally have to do this. And it's a lot easier to kind of see how it works when we're approaching a number rather than approaching infinity. But it can be generalized to all the other permutations. Okay, so looking at the derivatives, right, we're going to look at the limit as x approaches a of the two derivatives, and we're going to try and prove that that's the same thing as the limit as x approaches a of just the original two functions, f over g. Well, the first thing you do when you're taking a limit, right, is you plug in a. Well, the definition of f prime of a is, remember the difference rule? You take the limit as x approaches a of f of x minus f of a all over x minus a. Do the same thing for the g function. And because they're both, right, the product of two limits is the quotient of two limits is the same thing as the limit of the quotient, we can now kind of combine this as one limit of this quotient. And then because the top and bottom are being divided by the same thing, that goes away, and we're left with just this piece. And because we're doing the case where f of a equals g of a equals 0, right? These go away, and you're left with just a limit of f of x equals g of x. Now, it's more difficult to prove the general version, but you can see how it works in this one case, and at least maybe you're a little bit more apt to believe that it works all the time, and it does. All right, let's see an example of how we can apply this. So we're back to the first one that we were looking at, natural log of x over x minus 1. Remember, we can't use our original techniques of factoring or dividing by the highest power of x because the top isn't a polynomial. So we're going to apply L'Hopital's rule instead, because the limit as x approaches 1, right, of the top is equal to 0, the bottom is equal to 0, so we have 0 over 0. When we apply L'Hopital's rule, we take the derivative of top and bottom. The derivative of the top is 1 over x. The derivative of the bottom is just 1. So now we have the limit as x approaches 1 of 1 over x over 1, right, which is just 1 over x. We go back to our first step, which is always just plug the number in. And when you plug the number in, you get 1 over 1, which is 1. And that tells us that the original function also has a limit of 1 as x approaches 1. How about indeterminate products, right? All of these first slides, we were talking about an indeterminate quotient, 0 over 0, infinity over infinity. What about a product? What about f times g instead of f divided by g? So let's say we have a limit as x approaches a of some function equals 0, and then we have the limit as x approaches a of some other function g equals infinity or negative infinity. Doesn't matter which, right? They're both the same. Then it isn't quite clear what's going to happen if we take the limit of their product, right? 0 times infinity. You'd like to think it's 0, but that's not always the case. And in fact, it might not even have a limit at all. Because once again, just like with our quotient, there's this struggle going on between f and g. We don't know which one is kind of bigger, which one's more dominant, which one kind of takes over when we get close to a. In this case here, if f wins, if it's the more dominant function, then the answer is going to be 0. But if G wins, the answer is going to be infinity or negative infinity. Or there could be some sort of compromise, and we can get another one of those things where the answer is actually a non-zero number, like 2 or a third or something like that. But in any case, when we're faced with taking the limit of f times g, and we have 0 times infinity, we call that just the indeterminate form of 0 times infinity instead of the indeterminate form of 0 over 0 and infinity over. You don't care. It's just another example of some weird limit, right? It's not a typical limit. It's not giving us a number. It's something odd. It's dealing with zeros and infinities. So we're going to be thinking whenever we see these types of things, hey, maybe L'Hopital's rule is going to help us here. Well, remember, if we have 0 times infinity, we can turn it into either 0 over 0 or infinity times infinity. Because if you have 0 times infinity, think about turning this into 0 divided by the reciprocal of this, right? If this thing is going to infinity, wouldn't 1 over infinity, see how this is still 0 times infinity because it's 0 divided by 1 over infinity, but isn't 0 over 1 over super large number, isn't that 0 over 0? And then you get the indeterminate form of 0 over 0. Or you could go the other way, and you could think of infinity divided by 1 over 0, right? We're just flipping this one, we're dividing by its reciprocal. And if you divide by 1 over really, really small numbers, then this ends up being infinity over infinity. So you can see that we can turn it into either of these two forms. Now what you're going to want to do is pick the one that's going to make the math the easiest. Let's look at an example to see what I mean. So we have this limit here, and the limit as x approaches 0 from above. And first of all, I'm going to stop and ask, why do we have to take the limit as x approaches from above instead of just as x approaches 0? And hopefully you're all saying because natural log of x is not defined for 0 and below. Remember, natural log of x is only defined for numbers greater than 0. So that's why we have to take the limit from the right hand side, right from above. Okay, but the first thing we always do when we're taking a limit as a number is we just plug that number in. The limit as x approaches 0 of x, right, is just this is 0. And then as we come closer and closer down to 0 from above, natural log shoots down to negative infinity, right? So we get that this limit ends up equaling 0 times negative infinity. And that is one of those forms of, oh, that's that indeterminate weird product thingy that I can turn into an indeterminate quotient, and then I can use L'Hopital's rule. So I can either turn it into a 0 over 0, or I can turn it into an infinity over infinity. Well, you want to think about which one's going to be easier. So we're basically just going to take one piece and divide it by the other's reciprocal. And our two options are either this one, right, natural log of x divided by 1 over x, or the other way would have been the limit as x approaches 0 from above of x over 1 over natural log of x. But think about trying, because now you gotta kind of look ahead. The next thing we're going to have to do is take the derivative. Well, taking the derivative of the top is easy. But do you really want to take the derivative of 1 over natural log of x? That's going to be horrible. The derivative of natural log of x is easy, but 1 over natural log, now you got to do, natural log of x to the negative 1, which involves doing the chain rule. It's not impossible, but it's obviously a lot messier than doing this one. So let's do this one instead. Derivative of the top over derivative of the bottom, right? The derivative of the bottom is x to the minus 1, which gives us minus 1 times x to the minus 2. And that's why we get minus 1 over x squared. When you, kind of clean it up, because this is x to the minus 1 on top and a negative x to the minus 2 on the bottom, or you can think about just multiplying top and bottom by x squared, and that's where you get negative x, And then now you let x go to 0 and you go, oh, that's simple. That's just 0. So that means that in the original function, right, x natural log of x, because this piece was 0 and this piece was negative infinity and our answer ended up being 0, that means that this piece ends up having the dominance as we get closer and closer to 0. It has more impact on the product of the function. Now here we're just talking about what I have already spoken about. You can go either way, right? You can make it a 0 over 0 or you can make it an infinity over infinity, and it's all about using the one that makes the math easier, and this way would be a lot worse than the other way. Okay, how about indeterminate differences? So we've looked at indeterminate quotients, right? Something over something. Indeterminate products, something times something, and now we can look at indeterminate differences, something minus something. So now we have that one function goes to infinity, the other function goes to infinity, and if we're looking at the limit of f of x minus g of x, we get the indeterminate form of infinity minus infinity, and you think, well, it could be 0 or it could be infinity. Again, it's this contest between f and g. It's all about which one's bigger, which one, is getting bigger quicker, and those types of things. But the idea is you want to turn it into a 0 over 0 or an infinity over infinity so that you can use L'Hopital's rule. Bottom line is L'Hopital's rule only works with 0 over 0 or infinity over infinity. So if you can turn anything into that form, you can use L'Hopital's rule, but it has to be that, right? You can't have 0 over 7, because that would just be 0, or 0 over infinity. Right? That's just weird. We would have to figure that one out. It's got to be 0 over 0 or infinity over infinity. All right, here's an example. As x approaches pi over 2 from below, what happens to secant and tangent? Well, if you plug them in, you can see that they both go to infinity. Secant is 1 over cosine, and remember cosine at pi over 2 is 0, so that is approaching, right, 1 over 0, which is infinity. Tan is sine over cosine, and as you approach pi over 2, the top goes to 1, the bottom goes to 0, and again you get infinity. So we get this indeterminate form. But we realize that there is a very simple, easy to see common denominator between the two, and that happens to be cosine. So if we rewrite this as a fraction by finding that common denominator, we now have 1 minus sine x over cosine x. Again, we look at what happens when we let pi over 2, right, x go to pi over 2. Sine of pi over 2 is 1. So on the top we get 1 minus 1, which is 0. On the bottom we get 0. We get the form of 0 over 0, and yay! We can do L'Hopital's rule, which means we just have to take derivatives of each and then reapply, right? Reapply the limit. Take the derivative of the top, you get negative cosine x, because the derivative of sine is cosine, but remember that you have that minus in front of it. So when you take the derivative, you're technically getting a 0 from this piece, 0 minus cosine x. And then that's why we end up getting negative cosine x, negative sine x. Those cancel, of course. We just get cosine over sine. We let it go to pi over 2. Cosine of pi over 2 is 0. The bottom is 1. And that gives us 0. And again, this is justified. We can do this. We can do L'Hopital's rule because when we just evaluate it normally, we get 0 over 0. And we have to have that 0 over 0 over infinity, or we cannot use L'Hopital's rule. We haven't discussed this, but what would have happened if we had done the derivative, and let's just say instead of this we got an answer of 0 over 0? What do you think we do now? Well, you just do L'Hopital's rule again and hope that something happens. You can apply L'Hopital's rule over and over and over again until you finally get a fraction that's no longer 0 over 0 over infinity or infinity. Usually it happens after one, but sometimes you have to take two or three derivatives until it finally something comes out of the wash and something goes away enough so that you no longer have 0 over 0, or things will happen. Usually you only have to do them once, but just know that you can reapply L'Hopital's rule over and over again until you finally get an answer. If you see that you are just going in circles and you just keep getting 0 over 0 or infinity over infinity, then you would have to use a different technique altogether. Okay, another indeterminate form is powers. So now we're taking the limit of a function raised to a function, and if again you just plug in the a and figure out what happens to each function, you have a couple different options. Both functions could go to 0, which means you're now left with 0 to the 0 power. One function goes to infinity, the other one goes to 0, and you get infinity to the 0. Or one function goes to 1 and the other function goes to plus and minus infinity, and you get 1 to the infinity. If you have one of those three forms, then we can still use L'Hopital's rule by doing some simple algebra first. In all three of these cases, right, you've got a function to a function. The first thing you'd want to do is take the natural log of that thing, because the natural log makes the power come down. And so then you get natural log of your answer is equal to g of x times the natural log of f of x. Right? Because in your original thing, you're taking a limit of the right hand side, and that's going to equal some number. We're just going to call it y. And then you take the natural log of both sides, and that says natural log of your answer is just going to be the g of x comes down, right? G of x times natural log of f of x. We can also write the function as an exponential, and that can help us with other things. Once we have this, we can now take the derivative of both sides. But in either case, once you have it in this form, you're going to have an indeterminate product of 0 times infinity. And once you have 0 times infinity, you can rewrite it as, right, something divided by 1 over something, right? And then it becomes 0 times 0 or infinity times infinity, depending on which one you flipped. Let's look at an example. So we've got all of this seemingly ugly stuff, taking x go to 0. So just like anything else, plug the number in and see what happens. Sine of 0 is 0. So we get 1 plus 0, which is 1. Cotangent, remember, is cosine over sine. So that's cosine of 0, which is 1, very good, over sine, which is 0. So we get 1 raised to the 1 over 0. 1 over 0 is infinity, and it matches this one here, our third version, 1 to the infinity. All right, so we recognize it as one of our indeterminate forms that we can work with. So we say that the limit of this thing is going to equal this, right? This y, sorry, this function is going to equal y. We take the natural log of both pieces, and now we just have the cotangent comes down, cotangent of x, natural log of this stuff. Now we can take the limit of the natural log of y, right, which we're basically, instead of taking the limit of the stuff, we could take the limit of y, right, because we just made a straight swap. We're just going to call all this stuff y. But then if we take the natural log of this, we now get this seemingly easier stuff, right? So now we're going to take the limit of that natural log of y, which means we're going to take the limit of this stuff. And you might be thinking, all right, what happened here? Where did this come from? Well, cotangent, right, is cosine over sine. Again, this gives us infinity, and then this is natural log of 1, and natural log of 1 is 0. So this is infinity times 0. That's one of our indeterminate forms. By taking, instead of this thing times cotangent, It's this thing divided by 1 over cotangent, and 1 over cotangent is tangent. And now on the top, if we take the limit of this, we're now getting natural log of 1, which is 0, all over tangent of 0, that's sine over cosine. Sine is 0 over 1. So now we have 0 over 0. Yay, it's L'Hopital's, right? And we can actually use L'Hopital's rule. Taking the derivative of the bottom gives us secant squared. Taking the derivative of the top, well, that's just going to require a little chain rule, right? We got to take the derivative of natural log, which is the derivative of the stuff all over the stuff. So there's the bottom, right? 1 over the stuff just goes there. And then we have to take the derivative of the inside. And the derivative of the inside, well, sine goes to cosine. And then the derivative of the inside, right? The derivative of this brings that 4 outside. And that's where we get this piece. 4 cosine 4x all over blah, 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 blah. And then we reevaluate. Plug 0 in again. Cosine of 0 is 1, right? So the top gives us 4. On the bottom, sine of 0 is 0, and this is 1 plus 0 is 1, divided by, okay, secant. Secant is 1 over cosine. At 0, cosine is 1. So we get 1 squared. 1 over 1 squared is 1. We get this whole thing over 1. So 4 over 1, which is 4, all over 1, 4. But remember, we've computed the limit of the natural log of y. But we wanted to know what the limit of y was, right? This answer was the natural log of y, the limit of natural log of y. To find what y is, we have to realize that y equals e to the natural log of y. So if this equals the limit of natural log of y, then e to that is going to equal the limit of y. So our answer is going to be e to the 4. And that ends up being the limit of the original function. I'll page back up so you can remember what it was. This one right here. So the limit of that thing actually equals e to the 4th. Okay, so what are the steps involved when we have a function to a function? Well, just like anything else, you plug your number in, see what happens. If you get one of these 3 forms, then you know you can do L'Hopital's. But before you do L'Hopital's, you have to unravel that exponential, right, that power thing that's going on. And you unravel it by taking the natural log. So you take the natural log of the function, which is now going to give you a product. Then you take the limit of that new product, check it once again, make sure that you get the 0 times infinity thing so we can do L'Hopital's. Take one of the pieces and change it into its reciprocal, it's 1 over, and then divide by that piece. So it's the same technique we used for when we just started with an indeterminate product. Remember to flip the easier piece, and the easier piece is really always going to be the non-natural log piece. So that's really going to be the piece you're always going to want to flip. Okay. Check your limit again just to make sure that you now have 0 over 0 or infinity over infinity. It should all work. If it doesn't, you've messed something up, so go back and double check your algebra. Okay, take the derivative top and bottom, because now that you have the 0 over 0 or infinity over infinity, you have L'Hopital's setup. Take the derivative and then reevaluate it again. If you still get 0 over 0 or infinity, take the derivative again and try L'Hopital's again, and do that over and over again until you get an answer. Once you finally get an answer, just remember that the real answer is always going to be e raised to that, because you just found the limit of natural log of your stuff, and you really want to know the limit of your stuff, right? So that's the set of things. Take the natural log, flip the non-natural log piece, make its reciprocal, then do the quotient of the natural log piece and the other piece, then evaluate that limit, make sure that it's still 0 over 0 or infinity over infinity, so you can use L'Hopital's. Go ahead and use L'Hopital's, which just means take the derivative top and bottom, get an answer, and make it e over that answer, and you're done. Okay, those are all the different types of indeterminate forms that are going to allow us to use L'Hopital's. We can also use L'Hopital's for some of the earlier things that we've learned as far as factoring out and things like that. But anytime you have 0 over 0 or infinity over infinity, you want to be thinking L'Hopital's. And anytime you have some combinations of zeros and infinity, differences, all these different kind of oddball things, just remember that they can all be morphed into a 0 over 0 or infinity over infinity. And that's it.